Hello, my name is Austin Gray. With support from the North Carolina Space Grant, I performed research to validate a passive wireless temperature sensor for high temperature environments. I also collaborated with Dr. Cheryl Xu and Dr. Fuguo Yan of the Department of Mechanical and Aerospace Engineering at NC State University, as well as the National Institute of Aerospace. The sensors developed will be used in structural health monitoring and engine health monitoring. In the figure here is shown the percentage of mechanical aircraft failures organized by subsystem. We can see that over 1/3 of all mechanical aircraft failures are caused due to the engine or structures. On the right are two examples of engine failure from September 2017 and November 2010. These two examples, as well as this figure on the left, reveal the need and motivation for engine health monitoring. In this figure is showing a traditional engine monitoring unit. However, monitoring engines is particularly difficult due to high temperatures, harsh environments related to gases and pressure, and rotating high-speed components. These extreme operating conditions pose a problem for the traditional engine monitoring units and traditional sensors, electronics, and wiring. However, one solution is passive wireless sensors. Specifically, we created a ceramic microstrip patch antenna sensor for this purpose. It has a shift in its dielectric constant, which is just one of its electrical properties with temperature. And the shift was observed during experiments using wireless interrogation. On the left is a schematic of the patch antenna with the patch on top and the ground plane on the bottom. Of interest is the patch length and width. On the right are two polymer-derived ceramic sensors created for a high temperature testing. In this figure is shown the experimental setup with the vector network analyzer for processing the data, the horn antenna to interrogate the sensor wirelessly, and the box furnace to control the sensor temperature. We were interested in the reflection coefficient, which is the ratio of the power received over the power transmitted from the horn antenna. The reflection coefficient was then plotted across frequency, as seen in the green curve, with the point of minimum reflection coefficient being the resonant frequency. In the figure on the left is the reflection coefficient plotted at different temperatures from 500 degrees Celsius to 1,000 degrees Celsius. In this figure, as well as the figure on the right, we can see that as temperature increases, the resonant frequency decreases. In fact, this is shown in the trend line as well. The trend in this figure on the right can also be used in later experiments to correlate the observed resonant frequency with the expected temperature of the sensor environment. This slide shows current experimental progress as well as areas of possible future work. Right now, the sensor has been fabricated and tested at room temperature and high temperature. However, future work will include aligning the experimental results with theory, replicating the experimental sensor results, validating the temperatures measured with the sensor with actual temperature measurements from other means, and improving the sensor sensitivity. Future application of these passive wireless temperature sensors to engine health monitoring will include placing them inside of aircraft engines. We will wirelessly interrogate the sensors and in turn wirelessly receive engine health information. This engine health information will pertain to damage detection and the decision-making process with maintenance procedures. Thank you for watching.